intelligent lighting. In the first of our 3-part series on intelligent lighting, we'll be looking at the very basics of simply plugging in a light and using lights that have built-in drivers and controllers. Connecting the light to a power supply and having it run continuously may seem like the cheapest option, but it really isn't. It'll generate a lot of heat, aging the LEDs, and degrading any other heat-susceptible components within the light a lot quicker. To maximise the lifetime of a light, it makes sense to have it on at the brightness required, only when you need it. LEDs versus alternatives. Light-emitting diodes haven't just made cars pretty, they've played a pivotal role in the evolution of machine vision as well. Historically, quartz, halogen and fluorescent lights were the most common sources, but thanks to improved intensities, control, cost-effectiveness and especially longevity, in most applications, LEDs have surpassed them. LEDs are great for precise control. Not only can you pick a very narrow specific wavelength of light, very quick on-off and brightness control is also achievable. Unlike the alternatives, LEDs don't take very long to reach their full brightness, enabling a much finer control of the lighting. Dimmer control. The intensity of some LED lights can be controlled directly without the need for a complete lighting controller. Depending on the technology, this can be via an analog 0 to 10 VDC intensity signal input on the light, or by using a pulse width modulation (PWM) controller, which is a way of achieving analog control using a digital signal. A PWM signal consists of 2 components: the duty cycle, which is the amount of time that the signal is on for during a cycle, and the frequency, how long the cycle takes to complete. Because this on-off switching happens so quickly, the output appears to behave like a constant voltage analog signal. Pulsing, strobing. Once you have control of when the light is on, the pulses, strobes, can be synchronized to when the product is in the right position. This control is achieved by anything that can provide a digital trigger signal. Typically, this is generated by an encoder pulse, product sensor or PLC signal, a software trigger, the camera itself, or any other device or software that can create a digital signal. Let's have a look at this digital timing diagram to help explain how it all works. When digital trigger pulse A is initiated, there can be a trigger delay, B, before the light is turned on for a duration of the pulse width, C. The intensity of the light can also be controlled using this signal. We'll be covering this in part 2 of this series. Integrated drivers. Some lights allow you to feed the digital trigger signal directly into them. This is because they have integrated constant current drivers. Overdriving. Running continuously at their specified current rating, LEDs output 100% of their brightness. It's actually possible to get even more out of the lights. If the current is increased and driven for very short pulses, you can overdrive LEDs. The lights with integrated drivers can also be put into overdrive mode, so that every time they are triggered, they operate at the increased current level. To prevent the LEDs from burning out, the amount of time that they are on, in overdrive mode, is limited. They also need enough time to cool down before they are active again. This ratio between the strobe and rest time is known as the duty cycle. Thanks for listening. Subscribe to our feed if you'd like to be informed when the next part of this series is launched. If you'd like to know which products contain the features we've just covered, click on the link in the footnotes of this page.